All right, in this third unit, we're going to start moving away from just messing around with these trigonometric functions and their graphs and their inverses and things like that. And we're going to start pushing towards building up some new trigonometric identities. Some of those will be kind of nonsense ones that we'll just play with and show that, hey, these work. These are things that are equal to each other. Some of them will be really important and helpful ones that we'll continue to use in this class, but then also in things like calculus and physics and stuff like that. So what we want to do to start is to just recap some of these basic fundamental trigonometric identities that we already know. So just make sure we're all on the same page. What do we know? Where do we get it from? Why do we know these things? And then what we're going to start doing is to verify some new ones. I'm going to be careful with the word choice that we use here. I'm saying verify instead of prove for a good reason. We're not going to do some formal proofs here, which is probably good news for people who have seen some proofs in geometry classes and stuff like that before. But we will do some work that will show that things are equal to each other, and so we'll present some good, solid verifications. That's all we'll say. Proofs are a little bit more formal than what we're going to need to do. And then throughout the way, I'd like to just show off some different methods and strategies that are going to be really helpful. I certainly am not going to go over everything that you'll ever need. So this is not going to be an exhaustive list of every possible trick that you need to know. I want to hit some of the main ones, some of the helpful ones, some things that'll be important later on in calculus and stuff like that. So we're just going to kind of build up a bag of tricks here that we'll be able to keep in our back pocket. So first, here's some basic trig identities that we should already know. We know the reciprocal identities. We know that our sine function is really just 1 over the cosecant function, and same thing for the cosecant function. It's 1 over our sine function. Similarly, we've got this nice connection with cosine and secant. And lastly, our tangent and cotangent functions are reciprocals of each other as well. And then we also know that we can rewrite tangent as a quotient of the sine function over cosine, and similar for cotangent, we can write that as the cosine function over sine, because it's the reciprocal of tangent. So these we just know. We have these from definitions of the functions and stuff like that. We also have these other identities, our Pythagorean identities, our even and odd identities we have. So hopefully these are helpful for us too. These really come from the unit circle. Well, like could have come from some right angle trig, but it's easy to see with the unit circle because our sine output, if we think about the unit circle, that represents the y value. So this is really y squared on the unit circle. And the cosine output really represents the x value on our unit circle. So we really get y squared plus x squared equals 1, which is the same thing. Same thing as x squared plus y squared equals 1. And this is just the definition of the unit circle. This is everything that we need to know. And then we got these other Pythagorean identities by just dividing, right? If we divide everything by cosine, for instance, we get a 1 and a tangent squared and a secant squared, 1 over cosine squared. And if we divide everything by sine squared, we get a cotangent squared and a 1 and a cosecant squared. Not in this order. I mixed up the order for whatever reason, but whatever. These even and odd identities, they've come more from once we got into the graphs of the functions. We can see this. If we think about what unit circle stuff is telling us, we know that our sine function has this nice odd symmetry where if you put it in the negative angle, you'll get the negative output. This makes sense on a unit circle because if we have our angle up here, we know that the sine function is giving us a y value. And if you look at the negative version of that angle, the y value is going to be reflected. And so this little picture tells us, hey, we've got this nice odd symmetry. For the cosine function, though, you'll notice that when we reflect the angle down here, the x value stays the same. And remember, cosine tells us the x value on the unit circle. So for our cosine function, we've got this nice even symmetry. And then we've got all the same thing with cosecant and secant because they're just reciprocals. Tangent, we have odd symmetry. Same thing for our cotangent function. You likely won't use these even and odd identities near as much as the other ones. You'll use the Pythagorean identities. You'll use these quotient identities and these reciprocal identities quite a bit. You likely will mainly use even and odd identities when we're showing some things together. So it's not a big deal if this is not a part of your bag of tricks. No problems. This is what we're up for. We're going to be verifying new trigonometric identities. So we're going to be presented with some sort of an equation involving trig functions. We'll have a whole bunch of stuff on the left side equals some stuff on the right side. And we're going to try and verify that they actually are equal to each other. So really, what we'll be doing is kind of being presented with this with like a question mark above the equal sign. It's not really going to be there, but you can think of it that way. And we're going to try and show, yes, these two things are actually equal. What's the difference between this and a proof? Proofs have a little bit more formality that we're going to skip. So we're mainly just going to cut right into the meaty part of all this stuff where we actually show that these are the same thing, and we're going to skip some of the formal framework assumptions that we need to state, all that kind of stuff. Don't worry about it if you've never proved anything before. You don't know what you're missing, so it's not a problem. Typically what we'll do is we'll work with one side of the equation to make it look like the other side. So maybe we'll just focus in on whatever here is on the left. And we'll do some stuff to it and see, can we get this kind of target answer out of this stuff that we're working with? Typically, people are going to take whatever is more complicated looking and mess around with that. We're going to try and make that match the easier looking side. So if this left side over here is very complicated, it's got a lot of terms, it's a big, ugly mess, but this is just like one little thing, like maybe it's just sine of x, then maybe we'll mess with all this stuff and say, all right, can we make this look like just sine of x? Sometimes people will ask this question, why shouldn't we just work with both sides and have them meet in the middle? Maybe apply some steps to this side, apply some steps to this side, and maybe they both end up matching up. We can make them both equal some other thing. Technically, that's not actually that bad to do, but we have to be really careful with it. Because sometimes we'll apply some steps that aren't actually invertible, and so then we can't actually go backwards, and we can cause all these problems and blah, blah, blah. And I guess that you probably don't really care too much about it. All I'll say is this. In our text, I forget if this one does or doesn't. I think they make mention of it and kind of vaguely say like, yeah, you could try that. But I think they also say stay away from it. Work with one side and make it look like the other. I think they do state that explicitly. And most texts will say that. Every now and then there'll be some that are like, it's fine to work with both sides and just make them meet in the middle somewhere. I'm going to stay away from it because there can be some problems. And if you want more details on that, feel free to just message me and say like, hey, what are some of the reasons that this is the case? Why can't we really do this? And I'll show you some examples where you can apply some steps and get both things to match up with the same thing, but they're not actually equal. A really easy example is if you just multiply everything by 0, it all goes to 0 and everything's messed up. So anyways, that's that. What we're going to do from here on out is just build some strategies, show off some examples, see if we can do this stuff. So, the first strategy, probably our go-to thing. We're just going to see if we can convert everything to sines and cosines and see what happens. All of our functions can be written in terms of sines and cosines, whether we're using reciprocal identities or quotient identities or whatever. So, typically, it's easier to have a nice strategy of saying, like, let's put everything in terms of a consistent function, and we'll just mess with those. So if we can consistently work with sines and cosines, that's typically helpful. We got some good intuition for how these functions work. So here's an example. Let's just do this. So what we're going to do is we're going to rewrite our cosecant function. We're going to say cosecant is really 1 over sine of x. And our tangent function, we're going to rewrite as sine of x over cosine of x. And then we're going to just see what happens. And you can probably already see it, to be honest. So, rewrite everything in terms of sines and cosines. We'll use a mixture of reciprocal and quotient identities on the left side. So we're working with this side here. We're going to try and make it match up to secant. So bang, there's our 1 over sine of x. Bang, there's our sine of x over cosine of x. Cosecant, tangent. Neat. And you can notice, I don't want to get too far ahead, that these sine of x's cancel out, right? Really what we're doing is we're saying sine of x can come out here. And if we just switch up the order that we multiply things on the bottom, move the sine of x over, then we really have 1 over cosine of x times sine of x over sine of x. That is really just equal to 1. So you're really left with 1 over cosine x times 1. So there's our 1 over cosine x right there. And hello, reciprocal identity, that's secant. Ugh, I'll just say reciprocal. I'm bored of writing on this already. Anyways, reciprocal identity, there's secant. So, hey, as stated, there we go. We verified this. Cosecant x tangent x is equal to secant x, just like we were saying above. that's what we've got. They're not always going to work like this, but this is a good strategy to just write things in terms of sines and cosines and then see what happens. Here, we saw pretty easily that these sine of x's were able to cancel out, and then we're just left with the stuff that we wanted. All right, it's your turn to do some things. I'm going to let you pause the video, and then we can kind of work on... I'm going to do the second one with you. The first one, I'll let you do by yourself because it's really, really similar to the last one that we just did. I'll do number 2 with you after you pause this video. So go ahead, pause it, and come back. All right, so let's take a look at this second one here. Hopefully you've got this first one figured out. Cosine of x times cotangent x. I'll write that as cosine x over sine of x plus sine of x. All right, so now we might go ahead and do some other things, right? We can say this is really cosine squared over sine x plus sine x. Maybe I'll add these things together, and that's suddenly cosine squared x over sine x plus, I need a common denominator here, sine squared x over sine x. That's what this term really is with the denominator of sine. Now we can add these things together. Cosine squared x plus sine squared x over sine of x. You might notice this numerator here. That is the Pythagorean identity. That's equal to 1. So there we go. 1 over sine x, and there's our cosecant x. Everything works out pretty nicely. And again, converting things to sines and cosines made this a little bit easier to see what we were supposed to do because we got that nice fraction of cosine squared x over sine of x, and that helps us know that, hey, we can add these together with common denominators. Cool. Here's another strategy, just doing some factoring. So if you notice that you can do some factoring, we'll keep an eye on that. Factoring, it can be really easy sometimes, but it also can be really, really difficult. So sometimes this strategy is hard to notice. Sometimes it's real easy to notice. I only apply it when it's easy to notice because when it's hard to notice, guess what? It's hard to know to do it. That is kind of a weird way of saying anything, but whatever. You'll see what I mean. So here, let's verify the identity here, and we're going to try and do some factoring. So what you might notice right off the bat, hey, there's some cosines on both of these things. So what happens if we just factor out a cosine on both of these terms? So notice on the left side, common factor of cosine x. We also notice that we have multiple terms on one side. This left side has lots of terms, and if we factor it, we can lead this difference of terms into a product of terms, and then we can get one thing. So anyways, here we go. We factored out our cosine. It was here and here. There it is. And notice that you're left with 1 minus sine x. That is a Pythagorean identity. 1 minus sine squared of x. Sine squared of x plus cosine squared of x is 1. So if you shuffle this around, if you take this sine squared and bump it over to the other side, we get 1 minus sine squared of x is equal to cosine squared of x. So this thing is really cosine squared x. So we'll substitute that in, and suddenly we can see here's everything. We've got our cosine x factored out. We switch this out. Pythagorean identity right here. And now we've got cosine of x times cosine squared. Obviously, that's cosine cubed. So, as we said above, cosine of x minus cosine of x sine squared of x is equal to cosine cubed x by just doing some quick little factoring. Here's an example that you can try. This one's really similar, but now what you'll notice is that cosine squared of x is the factor that you can pull out here. Cosine squared of x is going to get factored out, and see what happens now in the rest of this stuff. Hopefully it goes pretty well from there. Pause the video and actually try this one. All right, hopefully you're back. You'll hopefully notice, I'm going to skip a couple of steps here. I'll let you do all the rest of the stuff filling it in. I think it's useful for you to try. This is really cosine squared times tangent squared, right? And then we can use this idea of writing things in terms of sines and cosines, and that's going to give us cosine squared times sine squared over cosine squared. And so it's just going to leave you to sine squared. Again, fill in the gaps here. There's some steps that I'm skipping intentionally for you to really investigate. So take a look at those. Hopefully that goes pretty well for you. Here's another strategy, splitting up fractions. What we're going to be doing is basically this. You have two things over one term. I'm going to notice this upside down triangle shape where you can split this fraction up into two fractions with the same denominator added. Normally we go this way. Normally if you had something like x over 2 plus 1 over 2, we'd combine that to get x plus 1 over 2. But now we're going to go the other way, and we're going to say, hey, we've got some stuff, upside down triangle shape, bunch of terms on top, one thing on the bottom. Let's split it up in terms of a bunch of things with the same denominator. And sometimes that's a really nice strategy. So let's keep an eye out for it. We're going to verify this identity. And look at this, our patented upside down triangle shape. We've got some terms on the top, one thing on the bottom. So we're going to split this up. We're going to have these two terms, our cosine squared x over cosine squared x, and also our sine squared x over cosine squared x. So we'll split that left side up into those two fractions with a common denominator. Here they are, cosine squared x over cosine squared x minus sine squared x over cosine squared x. Notice this thing here is just 1. This is really sine of x over cosine of x squared, and that's just tangent squared, and bang, we've got what we needed. We can turn this thing into 1 minus tangent squared. So, as we said above, by splitting fractions, we can just notice that this just falls into our lap, right? Splitting fractions is a really, really helpful thing to do. I don't have an extra example of this. You're going to find a bunch. Again, you're looking for this upside down triangle shape. There's a nice picture of it. So keep an eye out for that upside down triangle shape. You can split fractions really nicely. Notice that if this was upside down, or I guess maybe right side up, so if this was flipped around, if we had something like this, that is not equal to cosine squared x over cosine squared x plus cosine squared x over sine squared x. Sorry, my handwriting's really bad today. But if you've got a right side up triangle, you can't split that up. You have to have one denominator on the bottom, because then we split it up into fractions with a common denominator. So let me get rid of this real quick so it doesn't confuse anybody if these notes get posted. So make sure that we don't do any of that kind of thing. Our next strategy, to just combine fractions together. So this is kind of the opposite of splitting up fractions. Maybe now we've got two fractions and we want to make common denominators and just add them together. We're going to make common denominators in the exact same way that you normally would. Just a quick little reminder. If we do something like, I don't know, 2/3 minus 7/8, we can make a common denominator by just multiplying these two things together. We'll say, all right, our common denominator is going to be 24. So let's just multiply 3 on the top and bottom over here, and 8 on the top and bottom over here, and we end up with 16 over 24. That's really 2/3, minus 21 over 24. That's really 7/8. And then we just subtract the tops. This is really 16 minus 21 over 24, or negative 5/24. That's what we're going to do, except we're going to be doing this with some algebraic and trigonometric expressions. So here we go. We've got a cotangent x plus sine of x over 1 plus cosine of x. This is starting to look more complicated already, right? I'm going to actually do a mixture of two things here. The first strategy said write everything in terms of sines and cosines. Let's do that. Let's go ahead and write cotangent x as cosine of x over sine of x. And then we'll use these two denominators to make a common denominator for these two fractions that we're going to be adding together. So here's what it's got without my ugly handwriting. So again, we're just using this nice quotient identity, and then we'll use common denominators. So we've got our cosine of x over sine of x plus sine of x over 1 plus cosine of x. I'm going to multiply this denominator over here on the top and the bottom. I'm going to multiply this denominator over here on the top and the bottom. And if I do that, I'll have a common denominator of sine of x times 1 plus cosine of x. I'm not going to distribute that right now, so you'll see what I mean. But I can do the distributive property on top. So I end up with cosine of x times 1 plus cosine of x times cosine of x. That's this stuff right here. And then I've got sine of x times sine of x. There's my sine squared x. So I can then push these together over the same denominator, and I've got cosine of x plus cosine of square root of x plus sine squared of x over 1 plus cosine x times sine x. And maybe you notice something. Maybe you notice that this right here, I want to get my highlighter tool. That's the Pythagorean identity. That's equal to 1. So, oops, I was going to do a green highlighter. I want a green pencil. So that is all equal to 1 by the Pythagorean identity. And so there's our cosine of x plus 1. Notice we've got a cosine of x plus 1 and a 1 plus cosine x. Those are the same thing. Cancel those things out. And we're just left with a factor of 1 on the top over sine of x. This is really cosine of x plus 1 times 1, I guess. So when you knock these things out, you're really left with this little identity of 1 over sine of x. 1 over sine of x, that's equal to cosecant of x by the reciprocal identity, reciprocal identities. So this one here is a Pythagorean one, and that pretty much gets us there. So, again, as stated, hey, we've verified this. No more examples, but just keep an eye out for any sort of addition or subtraction with a fraction on here. That's going to be really the thing that tips you off that we're going to be having to do this kind of thing. This is, I think, the last strategy that we're going to show, and basically we're just going to say multiply the numerator and denominator of something by the same thing. And this is kind of a vague one. Normally, we're going to use the conjugate. So I'll reference this by just saying, hey, this is going to be a conjugate one. What I want to do really quickly is just remind you about what the heck a conjugate is. If you've seen this before, you've likely seen it in terms of complex numbers. So you've probably seen things like 2 plus 3i, where I is that square root of negative 1. And you'd say the conjugate is 2 minus 3i. And the main thing that you're doing is you're just switching these signs. You switch the sign of the imaginary part. The reason that we do this, maybe you haven't seen this before, but the reason that we do this is because there's a really clever, quick little factoring pattern that uses the same sort of pattern. You've likely seen this kind of thing before. This is very easy. We probably don't have to multiply this out. We know what it is. It's x squared minus 9. It's that difference of squares. The reason is because if we do the distributive property, we get x squared plus 3x minus 3x minus 3 times 3, which is 9. And these middle terms cancel each other out. They add up to get 0. So the reason that we do it with these complex numbers is because the imaginary terms multiply by each other and then they become real, if you remember that. And then we get these weird middle terms of like 2 times 3i, so 6i, and then a negative 6i, and the imaginary stuff just adds up to 0. Anyways, this conjugate is a really nice trick because it's going to give us a difference of squares. Let me type that real quick. Difference of squares. And when we get this difference of squares, we're going to be able to typically do more stuff with it. Squaring stuff helps sometimes. I don't really want to give too much more away because you'll see it in this example. I'll try and show off in this example a little bit of a hint here. The hint is that we've got this weird denominator of 1 plus cosine x. There's a plus sign in here. That part doesn't really matter. But if you multiply this by 1 minus cosine x on the top and bottom, go back and think, you're going to get a difference of squares. It's going to be the first number squared minus the second thing squared. It's going to be 1 squared minus cosine squared. What could that be? You'll probably recognize it. Anyways, let's do it. So multiply the denominator and the numerator by 1 minus cosine of x. The reason is that we'll turn the denominator into 1 minus cosine squared, and then, hey, Pythagorean identity, if you hadn't seen that yet. Here it comes. So we're going to multiply the top. I'll say sine of x times 1 minus sine of x times cosine of x. I haven't done even that yet, but if we just multiply the bottom part out, maybe I'll write it out solely for you. This is 1 minus cosine x plus cosine x minus cosine squared x. And so these middle terms, just like they did before, add up to 0, and we're just left with 1 minus cosine squared x, which Pythagorean identity, that gives us sine squared of x. Now we can notice that there's a sine x on top. sine squared x on the bottom. We can cancel some stuff out. So we're just going to be left with 1 minus cosine x over sine x. And then, hey, we've got an upside down triangle. Let's split that fraction up. So we can use multiple strategies at once. Isn't this fun? 1 over sine of x, that's this term right here. And then we've got our cosine x over sine of x, bang, right there. And so we've got cosecant minus cotangent using reciprocal identity, quotient identity. So, as stated above, that weird fraction, if we use the conjugate here, so again, notice we switch the sign, we get this beautiful little difference of squares that really ends up being a Pythagorean identity. Because again, sine squared x plus cosine squared x equals 1. So if we take this thing and move it over, we get 1 minus cosine squared x equals sine squared x. So the difference of squares is super helpful here because we can force a little Pythagorean identity to take those terms away. So that's kind of nice. All right. So all we really need to do here is practice. These are some strategies. Our textbook covers these pretty well, and I think they have some more little hints along the way. So take a look through there. Definitely don't just take this video as like the gospel 100% truth of every bit of thing that you're going to need, because I probably didn't talk about every single thing that you can do. There are lots of little tricks that you can mess around with. These are the main ones though. So mess around with some examples from the text, get into the practice problems that I put up from the textbook, and just start practicing as much as you can here. I think it takes a little while to get used to recognizing what things to do. And so the more you practice, the more intuition you're going to get about what types of tricks to apply at different times. I know this is a pretty fast video with not a ton of examples. I left a couple of examples undone at the very beginning, so go back and try those ones out. If you want, just look at the empty lecture notes and see if you can recreate the ones that we've done here without looking ahead on them, because there are the answers on there. And then again, jump into the textbook and see what you've got. I think practice is the main important thing that you're going to need to do here. Practice is going to build intuition. So jump into all those problems, see what you've got, and I'll see you guys on the online course site with any questions that you've got. Thanks. Good luck, everybody.